All right, hi everyone. Welcome to lecture 26. So in this lecture, we're going to prove both versions of the fundamental theorem of calculus. And so these two fundamental theorems, or if you want to combine them, they kind of are combined to form like the fundamental theorem, I guess. But the two different versions basically say that, integration and differentiation are sort of like inverse operations of each other on functions in a certain sense, right? And you're used to this idea. You're used to sort of taking indefinite integrals and then and knowing that like the indefinite integral of a function is like an antiderivative of the function. And so, or if you integrate the derivative of a function, you just get like the difference in the values of the function, right? I mean, that's the whole basis of like how you're taught to compute things in calculus. So we're going to sort of prove that that's true in a rigorous way, and we're also going to actually phrase those statements in rigorous ways, because you probably haven't actually seen before a truly like rigorous formal statement of the fundamental theorem of calculus. So in this specific part, we're going to prove one of these two, right? The two versions kind of are dealing with, doing the operations of integration and differentiation in two different orders. So in this one, we're going to prove that if you start with a derivative and then you integrate it, you basically get the original function back or whatever. And in the other version, we would say that if you take the derivative of an integral, then you get the original function back in a sense, right? So, okay, let's state the first version of the fundamental theorem here. So this is theorem 34.1, or the first part, I guess. So fundamental theorem of calculus 1. Right, so in this one, it's, so if G is continuous on AB and differentiable on the open interval AB, and if G prime is integrable on AB, this bears some elaboration, which I'll mention in a second, then the integral from A to B of G prime is G of B minus G of A, as you would expect, right? So there's one little detail here. So G prime is, okay. This is basically, well, let's see. Right, because the thing is that G prime is only guaranteed to be defined. Well, I mean, really, it's only defined on the open interval AB in this setting, right? So what does it mean to say that it's integrable on the closed interval? Because it doesn't take values at A or B, right? But like, the point is that like, if you just define random values for G prime at A and B, like if you just think of G prime as an abstract function, right? Forget that it's the derivative, right? Forget that G prime came from taking the derivative of G. It's just a function, right? So once you get G prime, if you just extend it to the closed interval AB in any way, if you end up with an integrable function after that, so G prime is integrable on AB if it can be extended to an integrable function on AB. Because the thing is that like, if you extend it and you end up with an integrable function, then if you take the integral of that function, the number you get won't depend on how you extended it in the first place. So if you can extend it in even one way, if you can just define any two values for G prime at A and B, and get an integrable function from that, then you could have defined those two values however you want, and the integral will still be the same. So this integral is the integral of any extension of G prime to AB. So the value doesn't depend on the choice of the extension, which I'm not even gonna put it, I mean, I guess you could put a tilde over here. It doesn't really matter. I'm just gonna erase the tildes. To excessive, it's excessively pedantic. This is by an exercise, which I think we've kind of danced around this idea a lot by now. So yeah, I'm gonna leave that one be. I think it's exercise 32.7. Yeah. Okay. So yeah, definitely, you know, make sure you understand this, but you know, I think we've kind of, you know, in the discussions, we've really covered that idea pretty thoroughly, I think. Okay, so anyway, so that's just this like little technical detail about what it means to say G prime is integrable on the closed interval AB. Also, believe it or not, it's possible to have a function G that satisfies these hypotheses. So it's possible to come up, so this is kind of trivia, I guess. It is possible to construct a continuous G on some closed interval such that G prime exists on the open interval AB, but G prime is not integrable. Believe it or not, the construction is it's hard, so I'm not going to go through it. But these functions do exist, so pretty weird. Pretty weird. It's very exotic and very hard to visualize. But yeah, anyway, so we actually need to assume that G prime is integrable, which is we're not just assuming that for convenience. We actually have to make that assumption because it might not be true if we don't. So anyway, but so assuming that it is integrable, here's the proof. And it's actually surprisingly simple. So select partition P. So our goal is to show that the absolute value of the integral of G prime minus G of B minus G of A. Oops. Is less than epsilon for all epsilon greater than 0. So if we can show this is true, right, then that means the absolute value here has to be 0. So they have to be equal. So let's basically find a very good approximation of the integral from A to B of G prime, right? Meaning let's find a partition of A, B such that G prime P minus L G prime P is less than epsilon, right? So then consider any tk minus 1 tk subset of P, right? We know G is continuous on tk minus 1. Sorry, not subset of P. What am I talking about? Subset of AB. TK. And G prime, I mean, it's differentiable, right, on tk minus 1 tk. So by the mean value theorem, there exists an xk in the open interval tk minus 1 tk such that g prime of xk equals g of tk minus g of tk minus 1 over tk minus 1, right? And notice that we also have little m of g prime tk minus 1 tk is less than or equal to g prime of xk less than or equal to big M of g prime tk minus 1 tk, right? That's just like trivial because, I mean, xk is in the interval tk minus 1 tk, so of course the value of g prime has to be between the infimum and the supremum of the values on that interval, right? So then, right, the lower sum of g prime on P is less than or equal to the sum of g prime of xk tk minus tk minus 1 from k equals 1 to n less than or equal to the upper sum of g prime on P, right? And this equals, by the choice of xk, right? This actually equals the sum, k equals 1 to n of, g of tk minus g of tk minus 1 over tk minus 1. So these tk minus 1 factors cancel out, right? So we just get g of tk minus g of tk minus 1, right? And of course, this sum telescopes to form just g of b minus g of a, right? But this means that the absolute value of, yeah, well, let's say, all right. Yeah, okay, yeah. We also know that LF, what am I talking about? LG prime P less than or equal to the integral from a to b of g prime less than or equal to u g prime P, right? So there's this interval. So basically, right, the integral from a to b of g prime and g of b minus g of a both fall in the interval L g prime P u g prime P, which has length less than epsilon, right? So the absolute value from a to b, of the integral from a to b of g prime minus this number g of b minus g of a must be less than epsilon. So epsilon was arbitrary. That means the absolute value of the integral of a to b of g prime minus g of b minus g of a equals 0, which is what we wanted to prove, right? So there you go. That's the first fundamental theorem. Sorry, I shouldn't say there are two versions of the fundamental theorem. It's really more that there are two fundamental theorems, or rather two parts there are two theorems which sort of together constitute the fundamental theorem, because they're not really equivalent to each other. I mean, they actually are two different parts of the whole. But anyway, that's the first part here. And also, so here's a lecture question. So lecture 26, question 1. Why, oops, do we need to assume G is continuous in this, in the fundamental theorem of calculus 1? Okay, because obviously, right, if G is differentiable, that means G is continuous on AB, right? So why is the assumption of continuity there not just redundant, right? So yeah, just, go ahead and think about it, and make sure to include your answer in the last homework. Okay, so the answer here is pretty straightforward. If G is not assumed continuous on AB, then the values of G at A and B can be anything. So, like for example, we could have G be the function on the closed interval 0, 1, which is like, yeah, let's say 0 for x in 0, 1, and 1 for x equals 1. Then G, G of 1 minus G of 0 equals 1, but the integral from 0 to 1 of G prime, right? G prime of x just equals 0 for x in the open interval 0, 1, right? This is actually integrable, right? So, and the integral is just 0, but these obviously disagree, because you can just adjust the values of G at 0 and 1 however you want, and that actually messes up like the right. It doesn't change the integral, right? But it does change the expression on the right-hand side in the statement of the theorem. So it is important that G be continuous at the endpoints in order for the theorem to make sense. All right. So that will be it for this video. And in the next one, we'll look at like an application. So we'll look at how we can prove the formula for integration by parts just using the fundamental theorem. It comes pretty easily now. So yeah, thanks for watching.